Remember, you don't have to do all three types of symmetry tests. You don't have to do all or both of the odd even tests. Just the one it looks like. For odd even, again, go back to that definition of what odd and even is. If you can prove that it meets that definition, you win. Yep. Who needs more time? I see a couple pencils still scribble. Hearing no objections, here we go. Okay, y'all notice this is the same one that we did last time where we found X and Y intercepts and domain range, all that kind of stuff. So it looks like a big W. And if I'm going to prove symmetry, and I think it's symmetric to the y-axis, then that's the only one that I need to prove. I prove something is symmetric to the y-axis by plug in negative x. If I put in negative x, lo and behold, I get the exact same thing. If I want to prove that or support that numerically, then first I got to find a numeric that's actually on the graph. So whether you trace, went to your table of values, or just plug something in. I shove a 1 in there. 1 minus 8 is negative 7. I think 1 negative 7 is on my graph. So first I show that. Negative 7 is 1 to the 4th minus 8, 1 to the 2nd, negative 7 is negative 7. Okay, I've shown that this is on my graph. Now to prove that it's actually symmetric, I go put its evil twin in there. I'm going to put in what? Okay, so 1, negative 1, negative 7. So I just still negate my x. It's just now there's a number there. And we check, negative 1 to the 4th minus 8, negative 1 squared. Sure enough, negative 7 is still negative 7. I win. Make sure you actually say what it is, not just the proof on there. Symmetric with respect to the y-axis. Okay. Prove odd, even, or neither. If it's symmetric to the y-axis, which of those is it? Even. So proving that it's even is very, very similar to this. Oh, Frank, that is not even remotely what I said. I have g of x is this, so I'm going to plug in a negative x, getting negative x to the 4th minus 8 negative x squared, which is x to the 4th minus 8x squared, which was the exact same thing. So g of negative x is g of x. I have shown that if I plug in a negative x, find g of negative x, I still get my original g of x. So I'm going to say you got your number support, algebraic proof, you actually said what it was. You got your algebraic proof all the way down to the end. Like that is the key to it. And you said it's even. So say it, save it, prove it, prove it, prove it. 5 things, 5 points. Again, make sure that you are labeling these. The packets and notebooks and stuff that were turned in last week that I was able to go through. So far, everything looks relatively organized. Good job. Last semester, especially some of my Algebra 2 crew, not always organized. And it made it a pain to dig through everything and find stuff. And then y'all know what it's like. If it's not going to be easy, we procrastinate. So I appreciate y'all labeling them, even if it's in a separate notebook or something. Again, I'll always do the notebooks first. Speaking of, there's 2 notebooks over there. If someone turned those in, go ahead and pick those up because I got through the notebooks, but not necessarily the entire stack of packets. We started on them, didn't make it all the way through. So, no, there was no assignment. It was just going to be like 1, maybe 2 of those definition proofs. Like, that's all I was going to do. And then by the time about 4:30, 5 o'clock rolled around and I remembered, I was like, screw it, they got it. Like, if we do okay with it, I don't really see a point in adding that extra practice. But sometimes I'm going to say, yeah, we need practice. Okay. And again, that's why I'm actually checking the assignments, as small as they are, this semester. It's because last semester I ran that experiment. I gave everyone the choice, and I saw a definite decline in fluency. As soon as I said it's optional, there was probably only 2 or 3 kids in every class who decided to do it at all. And we saw a difference in performance. So it's not about I don't get it, it's about how fluent am I with it. Okay? So there was an assignment, doesn't mean it's always going to be that way. We left off with limits. Remember, limits and continuity. Limit kind of acts like a coordinate, and y'all might have seen that. No, don't do that. Y'all might have seen that in Algebra 2. I know for sure that Mr. Spear and I kind of write it like this when we talked about end behavior. Remember, end behavior was as you go all the way to the ends of the graph, what is it doing? And we would treat them kind of like coordinates. Maybe you remember seeing something like this. As x goes to infinity, this goes to 0. Okay, so that's kind of how he and I tend to write it in Algebra 2 because we know that kids are usually coming up. The difference is, as you get into PreCalc and you start discovering what a limit is, I write the limit of my function as x approaches infinity. It's still got those same features. You can still kind of think of it as a coordinate, but it's a kinda coordinate. It doesn't have to actually equal this value, it just has to get really close to it. Okay, so we talked about limits, and then we started the continuity test. There's 3 parts to it. Part 1. I gotta just plug in the number and see if it exists. Make sure it doesn't break math. Part 2. I'm gonna go find, well here, f of c. The limit of my function, see if that exists. And then step 3 is the duh. I got to make sure that this equals that. If it does all 3 of those things, I say it is continuous, and I have proven it's continuous. Now, most of the time, we can just look at the graph. Like, at 0, well, I'm pretty sure I have to pick my pen up. That is not continuous. Okay, but do you have the test? Do you prove it? Okay. After we get past chapter 1, you're never going to do the test again, besides, maybe a quiz, but the test part of it we're not going to worry about anymore. We're just going to know what the different types of continuity are. Or discontinuity, I should say. Remind me again, how do I get the 3? The 3 stooges. Asymptotes. Piecewise functions, careful. All thumbs are fingers, but not all fingers are thumbs. Right? To have jump discontinuity, you need piecewise. But that doesn't mean just because it's a piecewise function, it has to create jump discontinuity. And that one kind of threw us for a loop. We had 2 or 3 of you who were spot on, and everyone else kind of got scrunched eyebrows. How do I get a hole in my graph? Cancel or remove the factor. Literally, remove the factor. That factor gets Thanos snapped out. You're saying this one point is gone. Everything else is still there. So, here we go. Do the continuity test and tell me, here is my function. Is it continuous at x equals 2? So when we start, they're going to ask us specifics. They're going to say, is it continuous here? Later, I'm just going to ask you to identify all points of discontinuity. And you got to know those 3 things about where discontinuity is created. For now, they're going to tell us, test this guy. So start with f of 2. Does it exist? Plug a 2 in there. Does it work? Two, 4, 8, 6, 2, 1, 1. Yay! It passes the first part of the test. The limit. Remember, the limit says as I'm approaching it from both sides, as I'm getting really, 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 really close to x's 2, what is y doing? So, limit of my function as x approaches 2. And if you're not sure, that's where our calculator comes in. And, oh, we got stuff on here from last time. Second plus 7, enter 2. Was it 2, negative 3, negative 1? Yeah. Come on, Frank. Come on, Frank. There you go. 2x squared minus 3x minus 1. And I'm going to set my table over to ask, because that allows me to get as close as I want to the x value of 2. Okay, everyone remembers this, right? From Algebra 2, or maybe that was new to you, but you got it written down from last week. So second window brings up my table settings. I want my independent variable, or x's, over to ask, and I say, I want to get really, 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 really close to 2. So you can slowly approach 2 in your table. I can say, all right, I'm at 1. I'm at 1.5. I'm at 1.9. Said the emulator like hates this entire bottom section. 1.5. Get right, Frank. Okay. 1.999. 1. Now, remember what I said about these cells? They're only so wide. If I highlight this, it shows me what I really typed. If I highlight this, it shows me what it really is. Now, I don't need this other stuff, but this is showing as I'm getting closer to it, from -2 to -1, now it's positive, now it's closing in on 1, right? I don't have to have all of that. I could just put in 1 point spam 9s, go to the other side and say 2 point spam 0s, throw 1 at the end. Okay? I can just say, look at it on either side. Right? So this is how I find my limit. I just get really, really close to 2 on both sides, you know, and yay, it's 1. I know with this, that seems kind of childish or redundant, but that's because it's a basic quadratic and we've been doing these for a long time. The functions aren't always going to be something familiar. They're not always going to be something easy. So we just want to go through that whole process. And then you just see, does the function value equal the limit? It passes all 3. So what I say is it is continuous. I don't just say continuous and quit. I have to say continuous at x equals 2. And that's important because sometimes you'll have a function where it has discontinuity here, here, and here, but everywhere else it's continuous. So you have to say continuous where. Okay, that is it. This is all I need to see on your paper. You don't have to copy down all the tables. You don't have to graph it out. You get to do all the work right there on your calculator and just write this because that's your test. Okay? So don't overkill it. These both got two different flavors. If you don't know what the graph looks like, or if you're struggling with where you're testing it, then sketch the graph. But if not, you might be able to get away with just plugging in stuff in your calculator and seeing what happens. Run the continuity test on both and tell me, is it continuous at x is 0? Especially if we're not as familiar with different types of functions. Not a bad idea to put some stuff in your calculator or to sketch the graph. Oh, and I just plain spaced this. Which of you are signed up for ACT this weekend? One potato? Okay. I had it written down for this week, but me and Mr. Spear both forgot to put it in the announcements. We will have review likely Wednesday, Friday, Spartan time, and at least one of Tuesday, Wednesday, or Thursday after school. And you just kind of take your pick of which one you want to go to. It is strongly recommended that you take your ACT immediately after your junior math class. And we go a little further and say after pre-calc for sure. I mean, kids will go up and take trig and calc and they kind of forget how functions work because they're deep diving on a specific subject. But right after pre-calc, you've just beat to death function analysis, so kids are usually pretty good. Yeah, it looks like we all got the first one for sure. I'd say the function of 0. All right, trace to... You know what, you could just do this all on the graph instead of the table settings. I didn't really think of it that way. Function of 0, I just trace to 0. Mom. So it passes the first part of the test. It exists. I don't care what it is. I don't care how ugly it is. I just care that it exists. Limit of the function as x gets really close to 0. Well, what if I trace to 0.000001? Y'all remember what this means? Scientific notation, 1 times 10 to the negative 27th. That means I'm going to move that decimal back this way 27 times. Fill them all in with zeros. What is that?
Basically.
practically 0. And if I go to the other side and say negative point, well, it says negative almost 0. So in both cases, as x approaches 0 from both sides, my y value is also approaching 0. And 0 equals 0, so all three aspects of it. This is your test, step 1, 2, and 3. And then you say it is continuous at x equals 0. In fact, because it's a polynomial, by definition, it has to be continuous. The other guy, though, we have a potential to have a asymptote. We also have the potential to jump from one to the other. So multiple types of discontinuity possible. It depends on where the rules overlap. And when I first showed the piecewise functions, was that last week? We just evaluated them. But both classes, kids started groaning when they saw piecewise. Because you remember graphing these, right? Where you kind of got to lightly do the entire graph, erase the parts that don't matter. Lightly do the whole graph, erase parts that don't matter. Okay, same thing. Now my calculator can't just erase the parts that don't matter. Well, you can, but you have to do some formatting stuff about conditional statements. I don't think anyone here has ever done that with their calculator, so I'm not going to bother showing you. Instead, you just got to be smarter than the calculator. I'm going to put in 1 over x, and what was the other one? Just x? Yeah, just x, the identity. Okay. Now, when I graphify that, it is going to graph them both. Be smarter than the calculator. When do I follow what? Okay. Says I'm going to follow the reciprocal function when x is less than 0. So that means this part doesn't matter. I am following yellow all the way up until x is 0. After that, at or equal to, I'm following y equals x, my blue line. So now this part doesn't matter. And it does say or equal to, so dot. That's what the graph looks like. So when I ask the function of 0, which of those two rules do I put in it? We talked about evaluating these. Y'all, caffeinate yourselves. Function of 0. Which of these two am I plugging it in? Okay, second rule, plug it in, it exists. But the limit of my function as x gets really close to 0, as I get really close to 0 this way, it's approaching 0. As my x's get really close to 0 this way, where do my y's go? Down to negative infinity. So because those aren't the same, I would say the limit does not exist. Now I can see that graphically. If I wanted to show that on my calculator by table, remember when I put multiple functions in, I'm going to see multiple things on my table. So I can say as I get closer and closer to 0, say I'm at negative 0.00003. I'm following the yellow one. As I get really, really close to 0 on the other side. 0.012. Frank? There. Now you got to be careful about these. There's a lot of kids who are going to see scientific notation, scientific notation. Oh, they're both going to 0 or infinity or something. They look the same. Be smarter than the calculator. I'm following the yellow graph all the way down to negative infinity versus I'm following the line all the way to 0. Okay, so you can look at the graph, you can plug values in, whatever your jam is. My test for this is function of 0 might exist, but limit does not exist because they're not heading the same place, and 0 does not equal undefined, contrary to freshman math. So then you got to tell me what kind of discontinuity it is. We have infinite, jump, or removable. And this is where we might get a little confuzzled because, wait a second, it hit an asymptote. But it also jumped from one rule to the other. Which of those is more important or relevant because of the type of function this is? The jump. Okay? Specifically, I'm not continuing on the other side of an asymptote because this asymptote is where this one started. I actually have a value where this asymptote was, so I'm not going to say infinite. It's the jump that made me hop from one to the other. So we say there is crisscross will make you jump. Jump discontinuity at x equals 0. Okay, so you don't have to have a ton of stuff shown to do your continuity test. Most of it's done on a calculator. All right, so more of it, but it's getting uglier. Those are easy. Determine whether it is continuous at the given x values, justify using the test. If it's discontinuous, tell me what kind. I got the graph over here just to show you what the graphs look like if you don't know, particularly piecewise. So if you want to sketch the graphs over here, great. If you want to look at it on your screen, also cool. First things first, I got to know what this looks like, especially a piecewise function. I'm going to follow this rule when x is greater than negative 3. So I got dot, I got slope, up 3, right 1, up 3, right 1, up 3, right 1, up 3, right 1, down 3, left 1, down 3, left 1, down 3, left 1. Okay, so that is this graph, but I only care about it when x is greater than negative 3. So I go to x is negative 3, all the way down, and I will put an open circle right now. And that is down 3 from there, so that's at negative 3, negative 11. So I'm going to follow that line from there off. Look like math dab. Okay. I'm going to follow this line everywhere before that. 2 minus x. It's amazing how many kids, even up into pre-calc, will see that and kind of go cross-eyed until you write it like that. Just because it didn't look familiar? Like when that one, I don't know, you come home and Dad shaved off his mountain man beard. I freaked out when Spear shaved his off last semester. Like, dude had just, it was like a Brillo pad. It was huge. And then I came in the next day and it was gone. It freaked me out. It just looks a little different. It's okay. Starting to. Slope is -1. So down one, over one, down one, over one, down one, over one, down one. Okay. Putting on auto tune, make millions. I keep repeating the same thing. But I only care about this graph from -3 back. So I go to x is -3. I make that a closed circle because it says or equal to, and I follow this line. Everything else doesn't matter. That's what my graph looks like. So now answer their question. Is this continuous at x equals -3? Well, can I plug in a -3 and not break math? Yeah, plug in -3. What do you get? First of all, which rule does it go into? First or second? Right? Or equal to goes in the second one. I'm going to get a 5. Yay! I can plug it in. That doesn't break math. Next, limit. The limit of my function as x approaches -3. Well, as I come at -3 from this way, and as I come at -3 from this way, do they do the same thing? This guy approaches 5. This guy, oh, screw you, Frank. Fine. This guy approaches -11. Those are not going to the same place. Like, this is the meme, you know, we are not the same. So if they're not the same place, then the limit doesn't exist. You'd say, no, limit does not exist. So it fails second part of test, which means it's going to fail the third part of the test. 5, last I checked, is not equal undefined. That is your test, 1, 2, and 3. What type of discontinuity was it? Piecewise will make you jump, jump. And again, you say it was jump discontinuity, but you also say where. Okay, at x equals -3. The importance for that is, what if I did the test at +3? Can I go through +3 without picking my pen up? Right? Function of 3 exists. The limit of 3 exists. Those are the same number. It would be continuous there. So whenever you state that discontinuity, you have to state where it's happening. Okay. Y'all remember what this looks like? Dump it in your calculator. It is not scary. No, it isn't. If we don't know what it looks like, dump it in your, gaze into your crystal ball and see what it's going to look like. Okay, it's another one of those rational functions where we have x and, oh, nope. That's all. X squared minus 9. There we go. If you remember from last semester or whenever you took Algebra 2, whenever I have a rational function, the very first thing I need to do, factor, friggin' factor. So I'm going to call that f of x is x plus 3 and how do I factor x squared minus 9? Difference of squares plus or minus the factor or the squares. So I'll have x plus 3, x minus 3. Which is why when you graph it, what you're going to see on the graph is 1 over x minus 3. So it's going to have a vertical asymptote at 3. And then 1 divided by thing is 1 divided by 1 is 1. 1 divided by negative 1 is negative 1. Like this. It almost looks like this. Does anyone remember? The whole. We said last week, your calculator will not show the whole. Y'all got it on your calculator screen. Hit trace negative 3. And the y is just blank, isn't it? Yeah. Because Thanos snap. It's gone. Okay? Yeah. So you got to be smarter than the calculator. Back here at negative 3. No. Stop that. I said black. There you go. You got to be smarter than the calculator and understand that there is a hole back here at negative 3. Okay, now do the tests. We got 2 of them. Test number 1. They want us to test at, what was it, plus or minus 3? Okay. Function of negative 3. When I plug negative 3 into not my simplified version, the original, always back to the OG, plug negative 3 into the original function, what happens? Divide by 0. You can't do that. Okay, so we already failed that part. However, the limit does exist. Because as I get closer and closer to negative 3 from both sides, doesn't it look like it's going to the same point? Yeah. Just realize, like, all of these math videos, me pacing up front, it's going to look like I'm up here doing this the whole time. Is math for me? When you plug in negative 3, does anyone remember the trick? How do I know exactly where that hole was? I think I heard it. Plug it in, right? I plug it into what's left. See, I Thanos snapped out x's negative 3. Well, look at the graph that's left. If I plug a negative 3 in there, I get negative 1/6. Doesn't that look like about negative 1/6 of a unit? So it does approach negative 1/6 as a limit. Now, if you didn't remember that trick from rational functions, and we will do more with rationals later, I would go to my calculator screen. Well, I would clear and clear. And it was x plus 3, right? X plus 3 over x squared minus 9. Okay. Table. Enter. No. Delete. There you go. If I want to get really, really close to negative 3, I'm going to type negative 3 point. Get really, really... Okay, we got too close. 3. Fine. Be that way, Frank. Okay. Now, if you get close enough to the hole, without apparently getting too close, it'll actually tell you what the value is. Not always. Say I was in decimal mode. Y'all know you can swap your answers, right? Where if it's on auto and I type it as a fraction, it'll give it to me as a fraction. Now what happens when I see this and I have no idea what it is? The calculator doesn't tell me it's negative 1/6. Y'all know you can go back to the main screen, spam sixes, and hit change to fraction, right? So if I don't know what that is, I go back to the main screen, say negative 0.1 math, change to a fraction, cross fingers. Okay? So if you're ever doing this table stuff and trying to get really close to a value and you're not 100% sure if it's rational or not, you can always go back to the main screen like this and try to change it back to a fraction. Or if you remember this trick, you plug it into what's left. I did the thing last I checked. Undefined does not equal negative 1/6. So it fails that one. And what type of discontinuity do we have at negative 3? I removed the factor. There's a hole. So I say there is removable discontinuity at x is negative 3. How's about over at positive 3? Plug 3 into, remember, the original, not the new one, not the simplified version. Plug 3 into the original. What happens? Divide by 0. Thou shalt not. So we have already failed the first test. Limit. As x approaches 3. From the left. So I'm at 2.99999. I'm at, from the right, 3.00001. And I see one of them is headed up to infinity, the other one is headed down to negative infinity. Those are not the same place. The limit does not exist. And if you saw the graph, you would just know that, because look at them. So I say the limit doesn't exist. This is one of those rare instances where ugly equals ugly. No, it does not pass that part of the test because you can't actually say undefined equal to undefined, like it's not a value that you can plug in. So it fails on all 3 accounts, and I say, what type of discontinuity do we have over at 3? We have infinite, jump, and removable. Infinite because we hit an asymptote. So infinite discontinuity at x is 0. Now, I put the graph up here, but look at everything. It was all done on the calculator. All you need to have on your paper, you would say like number 6. What? Did I say? Oh. I did put that one up from Friday too. Where's my marker? Well, see if we can get a 2-for-1 option. Jacob, how many we at?
If he gets this wrong, you should give him a big You have 5 left.
Bro, we got to get to 20.
We have to get, oh, we're adding?
You meant, what do you mean? You meant what?
It's okay. You gotta get 10.
11, close. But, all right. Now we're just picking on them. All right. Both of these, they've got different flavors. They tell you where to test it. Again, all you got to write on the side there is your test. Function, limit, do they equal each other? And then what type of continuity or discontinuity does it have? Like 4 lines of text, and that is everything. Okay, if you don't know what the graph looks like, dump it in your calculator. Might be needing that to find your limit anyway. This one looks like that 5th grader who got kicked off the bus for mooning Shannon Sand as it drove away. Looks like pressed ham. And then she ratted me out and got kicked off the bus for 2 weeks. We're speaking a lot in euphemisms, Izzy. It looks like a butt crack. The graph. Oh. Okay. The function value, the limit, do they equal each other? What type of discontinuity? That's it. Those 4 things. If you swap zeros and O's, you just sound like a 6th grader trying to make a screen name.
Yeah, but you still understand it. You can tell that it's still a circular shape.
Noob.
But you still understand the idea.
Yeah, but those should just be uppercase.
Exactly.
Those are more round.
They're all round.
Now they have eyeballs. In the mouth.
That's what it is, right?
And he's angry. 2 different.
All right. This one. Does it exist at 0?
No.
No. I plug in 0, I divide by 0, I make a black hole. Don't do that. Limit. This is an interesting one. The limit as I approach 0. Mm-mm. As you get really close to 0 from this side and really close to 0 from this side, where are they going? The limit is infinity. Remember, I don't have to equal the value for it to be the limit. It just has to approach it. And then, in the fullest sense of the word, undefined does not equal infinity. So, there's my first 3 lines of text. That is my test itself, and you tell me what type of discontinuity it is. You say infinite discontinuity at x is 0. Y'all remember, the idea behind this is continuous means I never pick up my pen. I can draw the whole thing without picking up my pen. When I say function of 0, I'm asking, is your pen touching the paper at this point? No. I had to pick up my pen. The limit. Does your pen go to the same spot and start at the same spot? Yeah, it actually does. But because I had to pick up my pen, it's not continuous. Y'all know that's why we have cursive, right? Cursive is pretty much outdated and dead in the 21st century. Did you still have that one teacher who made you write everything in cursive? Probably in elementary school? Dang, dude. I mean, Mrs. Ward cracked me over the head with the rolled up spelling edition, so, right? Jesus. That ain't right. Standon's thing is just kind of the tennis ball. Like, that's just his shtick, so.
Throw the power out. Like, he almost threw. Yeah.
Didn't throw a tennis ball at Boone's face. Boone definitely deserved it.
Okay. Yeah. Mm. The whole idea behind this is whether you are continuous or not, whether you have to pick up your pen or not. I just have to prove it. All right. Will that whole thing fit on this graph without changing the scale?
No.
I'm just looking at 5x plus 4. That's a pretty steep slope.
No.
Kind of fits.
Kind of fits? How far off-road do you have to go?
I don't think you do. Well, no, maybe I can.
Let's take a listen.
Like you can get like.
At x equals
like,
2, 2, I'd have to go to 14. That'd be pretty far off-road.
Whoa.
Okay.
So it fits to me.
Yeah.
Well, it's on the screen.
Where are we?
Trace 2.
14, yeah.
No.
Okay. So I'm going to change my scale on here to go by 2s. And then I'll graph them. I'm going to change my y-axis to go by 2s and then graph them. Because otherwise it's going to be a little too far off-road for my taste. Okay. Graph both. Get your piecewise function on there.
listen.
Up 5 over 1. Up 5 over 1. And up 5 over 1. Down 5 over 1. Down 5 over 1. And when x is greater than 2. So, the first guy takes over way out there at 214, off into the wild blue yonder. Contestant 2, again, negative x plus 2, if you need to write it like that. Up 2, down 1, 1, down 1, over 1, down 1, over 1. Okay. So, I hope you got the right graph. I made my y-axis go by 2 so I can actually see the right portion of that. And you see what I mean by later, we're not even going to need the test. Like if I just ask at 2, is this continuous? No. What kind? Well, it's piecewise, and there's no asymptote. It jumped from one ear to the other, so jump discontinuity. We just have to make sure we write out that entire process. The function of 0 is, plug it in here, 2. Oh, function of 2 is 0. Dyslexic math teacher. So it fits the first part, but my limit to 2 is, the limit doesn't exist because as left side goes all the way to 2, it approaches 0. As right side heads to x equals 2, it approaches 14. Those are not the same thing. So limit doesn't exist, and 0 is not undefined. But every freshman who's ever done basic algebra and gotten 0 for an answer thinks it's no solution. So we'll say jump discontinuity at x is 2. Okay? Y'all okay with this? Like the continuity test? The big thing is limits.
Here's 12 at x equals 2. Thank you, Jacob. Very nice.
If I just gave you a function and nothing else, come on you. Okay, if we didn't put this here at all, and I just said, determine any points of discontinuity. Go. Okay, this one is on our paper. We already see that it's going to be 1 and 2. I'll walk you through it. Step 1, I see a rational. Factor, factor, friggin' factor. Maybe.
No, not. It wasn't on purpose. He's lying. I didn't walk you. Oh, it's one of those.
Wait, I think he needs some baseball instead.
He's looking for something.
Decrease verbalization. Whenever you see rational function, you always factor first because something like this might happen. We need to be smarter and understand, if I can do that, what feature does it create? So I have a hole at -1. It's always a 0 of this. If I were to plug a -1 into what is left, what do I get? Yeah. What type of discontinuity is a hole? So we should then be able to, the function of -1 is no. The limit of my function as x approaches -1, well, if I shove -1 into what's left, I get 1. Undefined does not equal 1. So I'll say removable discontinuity at x equals -1. I didn't even have to go to my calculator because I know what the function does. What other type of discontinuity would I have, and where would it be? Thou shalt not divide by 0. Do you see that these things are just gaps in the domain? So thou shalt not divide by 0, that means I've got a vertical asymptote at x equals -2. So the function of -2 doesn't exist. The limit of my function as x approaches -2. Do you know what these type of graphs look like? What do the reciprocal functions look like? The swoops? If not, could I just dump that in my calculator real quick and look near the 2 or -2? I'm going to see this. So as I get really close to -2, I'm hitting that asymptote. That asymptote, they're going in opposite directions. No. Ugly doesn't equal ugly because they're not real. They don't exist. And you say, what type of discontinuity at -2?
No.
X is -2 was what type of feature? This guy was whole, so I said removable. This guy was an asymptote, so I say infinite. This is what we mean by, if I just say, identify any points of discontinuity. You don't have to do anything else other than know what the function looks like. So in that space, let's pull one out of an orifice because those are all just given to you. For this guy, Identify any points of discontinuity. Tell me what type they are. I see a rational function. First thing I do, factor, factor, friggin' factor. That is a 14, yeah. I don't understand why we're whispering. You shouldn't be making any sort of vocal noises. Get wrecked, math student. Okay. See, I specifically wanted this one on here because if you put that in your calculator, you ain't seeing diddly. It's just going to show you a line. Well, what do I do with it? Specifically, if you're in the regular 10 by 10 grid, because you keep resetting your calculator, it won't show you anything, I don't think, on that screen. Or no, there'd be a tiny little bit down in the corner, I think. Yeah. Dude, I visual process by staring off into nowhere. The number of times that you look behind you like I made the throw ball motion near a dog. No, dude, there's nothing back there. Wow, creepy quiet. Okay, graph look like that. It's just going to look like a line. Going to have a hole way back there at -3, -20. Because this factors into x minus 17, x plus 3 over x plus 3. I understand that every time I remove a factor, there's a hole at x equals -3. When I plug a -3 into what's left, I get a -20. I understand that hole is discontinuity, so I say the function of -3, because that's where my discontinuity is no. My limit, as I get really close to -3, I can go into my calculator, I can type negative 3.00001, negative 2.999999. And in both cases, I'm going to get really, really close to negative 20. Undefined does not equal negative 20. It fails, passes, fails. Because it's a hole, I will say removable discontinuity at x is negative 3. So that's the difference between they're going to give you a value to test versus I just got to know what features create discontinuity and test there. Okay? Now, this other stuff about limits, intermediate value theorem. This is one of those lame things that we would have learned with our polynomial root theorems. All right. What happens when I plug in a number into my function and I get a negative? So I go to my ask and I put in this number and it tells me negative number. Then I go to this number. I say when x equals, 5, and it comes out with a positive number. What had to have been in between there? I went from negative number to positive number. 0 had to be between there, right? That's the intermediate value theorem. It says if I test here and I test here and they're opposite signs, there had to have been a 0 in between. Which is really duh in the 21st century because you're just going to look at your screen and you're going to say, I think it's about there. Right? So we used this in the ancient times to narrow down our possibilities when we remember like Descartes' theorem and the law of signs and that kind of stuff to narrow down all my polynomial zero choices. That's where this came from. I think it's redundant, so cross the whole thing out. It's just one of those things that intermediate value theorem sounds really complicated or smarty pants. You might see those words on an ACT. Y'all, it just means that, look here, there's a 0. Okay? Poke. So, yeah, that's the same thing, cross it out. There we go. End behavior. See, at the ends of your, shall we say, high school domain, on this end of the graph, freshmen. Freshmen act really dumb. They are very immature. Then, about halfway through sophomore year, the head starts to emerge from the opening. They get enough oxygen to the brain, and now they got life figured out a little bit. Halfway through sophomore year, things start getting okay. Juniors, that's usually where it's at. Like, they got stuff figured out. They're not terrible. They're not cocky yet. It's like Mama Bear's porridge. Then seniors. Seniors start getting a little bit a little arrogant, starting to strut around, and maybe get a little too full of themselves. And behavior. Okay. End behavior is what does it act like at the ends of the domain. Y'all know what kids act like when they're coming into and leaving high school. Well, those are the ends of the domain. End behavior is literally that, the limit of my function as x approaches. Now I'm going to say ends of domain because the ends of the domain aren't always plus or minus infinity. So that's why I'm saying ends of domain instead. Equals what? As my graph goes all the way to the right, what is it y doing? As my graph goes all the way to the left, what is my y doing? You may have just written these as, maybe back in Algebra 2, did you write it as x approaches infinity, y's go to negative infinity? Remember maybe writing it kind of like a BS coordinate like that? I know that me and Mr. Spear do that. As x's go all the way back to negative infinity, my y's go all the way down to negative infinity. Kind of like a coordinate. The only difference is now we're going to write them as limits. Okay? Now, if I want to know what that does, the easiest way to find it, if I don't have the graph itself, they say to support numerically. We're not doing that. They want us to have an entire table. Is type that into y1. y1. Clear. Negative x to the fourth. What's that? Plus 8? Yeah. Plus 8x to the third. Plus 3x squared. Plus 6x minus 80. Okay. Now, I could zoom 6. I could just look at my graph and say, well, it appears to go in these directions. Frank? Frank? Any day now, Frank. All right. I don't see the rest of my graph. Maybe I don't want to monkey around with the window, so instead I'm going to go to my table. I'm going to make sure I'm on ask mode, so I don't have to scroll on to infinity and beyond. And instead of repeatedly monkeying around with the table and getting larger and larger numbers, the way they want us to do it is have 0 in the middle, go to plus or minus 10, plus or minus 100, plus or minus 1,000, plus or minus 10,000. They want to keep going out like that. We're going to say, like theme music with it, y'all, if this goes out to infinity, I'm going to ask, what is my y when I do that? Negative 1 E72. What is that? Oh, you did a little too much, huh?
You're so funny.
All right. No, we're just going to combine the whole lot of you.
I just thought I get that.
Yep.
He's the one that did the 69, Dave. I did not.
There we go.
I have done nothing.
Y'all need to figure out what you're doing for food then. So this is negative 1 with 72 zeros after that. What is that?
A lot.
Negative gigantosaurus number. Negative infinity. So that's what you write for your domain. If I go all the way back to negative infinity, it also goes down to negative infinity, right? I don't need to do something super precise. I just need to say way out there. Okay? That's how you find end behavior. The difference between now and Algebra 2 is you're just going to write those as limits. So tell me, what does this do as I go all the way to the right and all the way to the left as end behavior? My limit of my function as x goes all the way out to infinity is what? My limit of my function as x goes all the way back to negative infinity is what? Now, maybe we think it looks like negative and positive infinity respectively. I'd put the function in and test it to be safe, because what if I don't see the entire function? What if they're only showing me part of it and this thing curls back up? Unless you remember enough about polynomials to prove to me why that doesn't happen. How do you know? Cubics have 3 zeros. If they got 3 zeros and I see all 3 of the zeros, then I know that this thing is never going to switch directions again. So as we head all the way back to negative infinity, my y's go to negative infinity. As we head all the way to positive infinity, my y's go to positive infinity. Same thing here. I'd say the limit of my function is, as we go back to negative infinity, the limit of my function as x goes all the way to infinity. Dump it in your calculator, spam 9s, see what happens. That's how you find end behavior. A lot easier. Okay. Tomorrow we'll pick up with numbers that don't go to infinities, and we'll move into 1-4, which is extrema, which should also be review. Y'all remember like relative minimum, absolute maximum, that kind of stuff? Should be easy.
That's a lie. You know exactly who that is.
You know, in the past, I have just posted a kid next to someone who's verbally problematic, given them like a Nerf bat, just said, you take care of this. You're in charge of them for the rest of the semester. In the middle of teaching, you'd hear